All right, now we're going to talk about something called simultaneity. That means, whether or not something is simultaneous. All right, simultaneity. Now we're going to talk about a nice example here. So basically, we want to investigate the properties of time in two completely different reference frames. Again, one reference frame is moving relative to the other one. We don't care about the other one. We just want to understand that one is moving relative to the other. That's all. Okay, so let's do it. All right, so here we have a rocket. And so the astronaut placed two lights back to back, and there's a target here and a target here. And these targets are both the same distance from the lights. Okay? All right. So, and the way this light works, when you turn it on, both, the pulses go at the same time, relative to the rocket. Okay? So you turn it on, okay? So that's how the light works, all right? So yeah, the light pulses are emitted at the same time. Okay, so here's the question. According to the astronaut who's at rest on the rocket, when do the light pulses hit the targets? So pause your video and figure that one out. Okay, according to I hope you understand, according to the astronaut, the speed of light is the same, right? The distance is the same, and so the time will be the same, right? And so each target will be hit. So this is what it looks like according to the astronaut, agree? So each target will be hit at exactly the same time, right? So we say that the targets were hit simultaneously at the same time. All right, that's cool. Now we want to say, when will the targets be hit from the mission controller, or whatever, back on Earth? Okay, so the astronaut was at rest relative to the rocket. The people on Earth are obviously not at rest relative to the rocket. So that's the question. When do the pulses arrive at the targets according to somebody on Earth? So this is what it's going to look like. Oh, sorry, I forgot to show you that. Okay, according to the astronaut, the pulses of light emitted at the same time will arrive simultaneously. Yeah. Okay, all right. So here's the other one. So this is what it looks like relative to Earth, right? So the lights are emitted, but remember, the rocket's moving to the left. Okay, so they were emitted here, so they travel the same distance, but the rockets move to the left. So which one's going to get hit first? Well, obviously, since the rocket's moving to the left, this target is approaching the light, right? So this one's going to get hit first. This one's going to get hit second, right? This one's already hit. This is not quite yet hit. Okay, make sure you understand that, all right? So, not simultaneously, right? Not simultaneously. So what's the conclusion? The conclusion is just because something is simultaneous in one reference frame, it's not going to be simultaneous in another reference frame, a different reference frame. In other words, right? We're saying it's a different reference frame if it's moving relative to the other one, right? S and S prime, Okay. All right? So if S and S prime are different reference frames, what is simultaneous in one reference frame is not going to be simultaneous in the other reference frame. Okay? So simultaneity is a relative concept because it depends on the motion of the observer. All right? That's kind of weird, right? I mean, usually, what do you usually think? If I clap my hands and if I do this, no, how about this? Sorry, let's do this. If I do that, you say they're simultaneous, right? But yet, what did we just see? If you were moving past me, you would say that they're not simultaneous. Kind of weird. Okay, so according to the mission controller, the two pulses emitted at the same time from the center of the rocket do not arrive at the ends of the rocket simultaneously. Okay, so here's a little follow-up. Which of the following statements about simultaneity is true? Events that are simultaneous in one reference frame are simultaneous in all frames. Two events cannot be simultaneous in two different reference frames. An observer can never measure two events as occurring simultaneously. So pause your video and figure it out. Okay, what did we just learn? Two events cannot be simultaneous in two different reference frames. Okay? All right, now we want to talk more about this business about time being relative. Okay? So we're going to investigate the properties of time in two different reference frames. Okay? Again, one is moving relative to the other. That's what we mean by two different reference frames. Okay, so this is not a quote. Let's say it's a paraphrase, all right? So time, according to Einstein, time is a physical part of the physical universe. Just as one can measure the properties of a stone or a beam of light, one can measure the properties of time itself. Woo! That's kind of interesting, don't you think? All right, let's do it. Okay. How do you measure time? Well, that's a silly question. With a clock, right? A watch, some kind of clock, you know? Well, if we're going to do an experiment, right? We're going to measure the time in two different reference frames. So we want to use clocks that are really simple, you know? We don't want to have any problems with friction or corrosion or, you know, you have to lubricate them or, you know, we don't want any, we just want to make these clocks as simple as possible. Now remember, we can use our imaginations, right? Okay, so we're going to use something called a light clock. Completely simple in our imaginary world. All right, here's a light clock. This is a mirror. Perfect mirror, of course. This is a perfect mirror. That means they're perfectly flat. They're also perfectly, this one is perfectly parallel to this one. And they're 150,000 kilometers apart. So yeah, I know it's not practicable. Who cares? Now, what's so great about 150,000 kilometers? Well, what's the speed of light? Speed of light is 300,000 kilometers per second. So, what's going to happen here? So we turn the thing on, right? And let's go 1 second, 2 seconds, right? Because you know, the total travel time is 300,000 kilometers, right? And the speed is 300,000 kilometers in a second. So every time it goes up and down, it's 1 second. Okay, so perfect, right? We don't have to worry about friction. We don't have to worry about like a spring or electronics or the battery dying or, you know, rust or anything. It's a beautiful clock, right? Super accurate and wonderful. All right, just because it's a little impractical, we don't care. Okay, so here's the experiment. All right, so we have two people, Velma and Mort, okay? So Velma is in a rocket, and she has a light clock. Awesome. So she pushes the button, and it goes up and back. So Velma says, you know, 1 second. No kidding. So Velma, 1 second. Now, is she right? Of course she's right. All right, so that's from her reference frame. All right, now let's switch reference frames. Let's go to Mort. Now, Mort's just standing still on the earth, so he sees Velma zipping by to the right. Now, what does he see, though? You know, Velma, according to her reference frame, the photon just went up and straight down, right? But Mort, you know, the rocket's going to the right. So it's kind of like this. So relative to me, like this, right? But if I'm moving relative to you, what does it look like? It looks like this, right? So according to Mort, what he sees the light go this way, reflect, and then go that way. Agree? Now, remember, everybody measures speed of light, the speed of light. And we also know that distance equals speed times time, right? So, obviously, you know, this is 150,000 kilometers. Well, what's this going to be? Well, it's certainly going to be more than 150,000 kilometers, right? So this here is certainly going to be more than 300,000 kilometers. But remember, speed of light, speed of light. So if this distance is greater, according to Mort, than this distance, doesn't this time have to be longer than 1 second? Well, of course, right? Distance equals speed times time. The distance that Mort measures is much longer than the distance that Velma measures. Speed of light is the speed of light. Here, let me put a C here. Right? So the time that Mort measures has to be more than a second. So Mort says more than 1 second. Is he right? He's right. Is Velma right? She's right. They're both right. Time is relative. Okay? So we're concentrating on Velma's clock. Velma says 1 second. Mort says more than 1 second. Mort says, Velma, your clock is crummy. It's running slowly, right? Because he measures maybe 2 seconds or 3 seconds, and she just measures a second. So Mort says your clock is a piece of junk, But wait a second. I mean, they're both right, because time is relative. All right, let's do it. Let's do it again. Just switch it. Let's switch it this time. Now we're going to concentrate on Mort's clock. So here's Mort's reference frame, right? Up and back, right? Okay, so Mort says 1 second. And he's right. 1 second. But what does Velma see now? She's the one zipping by, right? So she's going to see this thing again, So Velma's going to say, well, it's traveling further, than 300,000 kilometers. Speed of light is speed of light. So the time has to be longer than 1 second. So Velma's going to say more than 1 second. So now we're concentrating on Mort's clock. Mort says 1 second. Velma says you're nuts. It's more than 300,000 kilometers, so it has to travel. So it has to, more than 1 second. So now Velma says, Mort, your clock stinks. It's running slowly. Okay, so Mort says, Velma, your clock is running slowly. Velma says, Mort, your clock is running slowly. Who's correct? They're both correct. What? They're both correct. Time is relative. There's your time and there's my time. And they're different if we're on different reference frames. Kind of weird, right? Yep. But it's true. Okay. Now, this is a really awesome graph. So this is the time. Okay, let's concentrate on this one. Okay? So Velma is always going to say 1 second. Agreed? And Mort is going to say more than a second. But what he's going to measure depends on the speed of the rocket. So let's go to that graph. Okay, so here's the graph. So Velma always says 1 second, right? This is what Mort would measure for the time. And you can see it depends on the speed of the rocket. And notice it says like 0.1 c, that's 1/10 of the speed of light, 2/10 of the speed of light, right? So we're down like here, just a little bit to the right of 0. And so, we never measure these kinds of really neat things with our rockets or missiles or, anything, planes or whatever, But this is awesome. So in other words, if the rocket was going like at half of the speed of light, Velma says 1 second. Mort would say, no, more like almost 1.2 seconds. But look how it goes up. Let's say the rocket was going 90% of the speed of light. Well then, Velma says 1 second. What does Mort say? 2.2 seconds. Let's say it's going like at 0.999. Well, sorry, it doesn't go up that high on our chart, right? So all I'm saying, when things go really, really fast, the time changes really, 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 really rapidly, right? Okay. You can click on this if you wish. I'm not going to right now. This is just it's on Wikipedia, the list of vehicle speed records. It's just worthwhile clicking on that just to see that, our fastest missiles, planes, rockets, whatever, their speeds are nothing compared to the speed of light. All right? Here, for the Americans, right, speed of light is 186,000 miles a second, 670 million miles an hour. I mean, think about it. It's incredible. Okay, so this is nice to have a graph, but we want an equation, right? And it turns out the equation is not difficult, just algebra, Pythagorean theorem. So let's do it. Well, actually, you're going to do it. Okay, so here we go. So there's our light clock, right? But now we're going to be a bit more general. We're not going to say, because before we had 150,000 kilometers, right? Now we're just going to say H, right? H, okay? So that's Velma. Let's say whatever, doesn't matter. Okay? So here we go. So this is frame S prime. Okay, so we want the light to go up and back. And remember, distance equals speed times time, right? All right, so the distance up and back, 2h. So we have 2h, speed is c, and the time, since it's a frame S prime, so I'm going to say delta t prime. Okay? So therefore, because we're looking for time, you know, so therefore delta t prime equals 2h over c. We're going to use that again, all right? Okay, so that's what it is in S prime, but now we want to see what it is in S, because that's what we're doing, right? We're comparing time in two different reference frames. Okay, so there it is, right? That's what, you know, Velma just sees, woo, woo, but Mort sees it go like this, right? Okay, so here we have a right triangle, right? So, so this is S. So S, let's just look at the right triangle on the left, you know, this one, okay? So Pythagorean theorem, okay? So, and you notice this is 1/2 v delta t, right? Because from here to here is delta t, right? And it's going, the speed is v, so this is half the distance, so it's half v delta t. So Pythagorean theorem, that squared plus that squared equals that squared. So let's do it. So v delta t over 2 squared plus h squared equals c delta t over 2 squared. Okay, now what I want you to do is solve for delta t, okay, in terms of v over c. Okay, so in other words, you're just going to do some algebra, you know? You're going to get an equation. Delta t equals something, but the something I want you to have, you know, terms of v over c in your answer. Okay? It's not going to take you very long. So pause your video. You got to get used to doing this, all right? So pause your video and do the algebra. Solve for delta t in terms of v over c. So do that, please. And you'll use this. Okay, what you should have now, if you've done it correctly, you should have delta t equals 2h over, let me write it like this, 2h over c all over 1 minus v over c squared with a square root on the bottom. That's what you should have. Make sure you can do that. You're going to get used to doing this kind of algebra for this relativity stuff. Okay, now again, what's 2h over c is delta t prime. So you have delta t prime over square root 1 minus v over c squared. Okay, now for whatever, okay, so what do you notice? What do you notice? Delta t is not the same as delta t prime. Remember we talked about that in a previous slide? Okay, that's the thing. Same events, different time. Time is relative. Delta t is not equal to delta t prime, right? You have this thing on the bottom, okay? Now, for whatever reason, Randy Knight doesn't like to use delta t prime. He wrote the book. He can do whatever he wants to do, right? So delta t prime, he says, is delta tau. That's that Greek letter tau, you know? So he just uses delta t prime to be delta tau. So you just have this then. Okay? So it's not a big deal. You just got to remember it. So delta t prime, he just uses tau. All right? It's just a dumb thing to call it. Okay? Now, so that's important. Yeah? I mean, there it is. Just a simple experiment. And we show that delta t is not equal to delta t prime. So delta t equals delta tau over square root of 1 minus v over c squared. Okay? Now, notice something, by the way. How come we never notice this in our everyday life? Well, because in our everyday life, v here is much, 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 much less than c. So this thing is basically 0, right? So if this is 0, what do we end up with? We end up with delta t equals delta tau. Yeah? And that's what we see in our world. But if we were going at nearly the speed of light, this would become important, you know? So that's why, again, look at this graph. You know? When we're down here, the times are the same, right? 1 second. It's only when you start getting, you know, a tenth of a speed of light, 20% speed of light, you know, especially up here, that's when you start noticing the differences. Okay? So this equation, so this graph is a graph of this equation, all right? This equation. And it's nice to have the equation, you know, because, I mean, this graph is not so great, you know, kind of dies. I mean, it doesn't show us anything up here, right? But if we use this equation, you know, we can get anything we want. So it's pretty awesome, okay? Okay, now, look. If you do relativity for a while, you get really sick and tired of writing v over c everywhere. You also get sick and tired of writing, okay, hold on just a second. Let me just show you something. This is the same thing as writing 1 over square root 1 minus v over c squared times delta tau, right? I mean, just algebra, right? Okay. So anyway, if you do relativity for any length of time, you get sick and tired of writing v over c. You also get sick and tired of writing 1 over square root of 1 minus v over c squared. So, since physicists are incredibly lazy, really means efficient, we come up with easier ways to write this. So from now on, v over c is beta, right? The Greek letter beta, you know, alpha, beta, gamma, and all that, all right? So whenever you see a v over c, write beta. So this is 1 over square root of 1 minus beta squared. But come on, I don't want to write this all the time. It's a waste of time. So this is gamma, all right? So this is beta, v over c. You might think this is crazy, but you wait until you start doing your homework. You're going to appreciate this. So v over c is beta. 1 over square root of 1 minus beta squared is gamma. And you're going to be solving for gamma all the time when you do your relativity problems. You'll see. Okay? Now notice, let's go back to this gamma. Okay, so gamma is 1 minus beta squared minus 1/2 power, right? However you want to write it, you know? Okay. Now, let's look at it like this. Maybe it'll be easier. Okay. Now, beta is always going to be less than or equal to 1, right? I mean, for a photon, it's equal to 1. For anything that has mass, okay, anything that has mass cannot travel at the speed of light. It has to be less than the speed of light. So for any massive particle, beta is always going to be less than 1. For a photon, beta is going to be 1. Okay, so you notice that, what's this denominator? This denominator is always going to be less than 1, right? So what's gamma going to be? So gamma will always be greater than 1, right? Gamma will always be greater than 1. So you kind of want to remember that, right? Because if you get a gamma that's less than 1, you know you goofed, all right? So gamma is always greater than 1. Okay, let's go back to our equation. So we figured that out, but we hate writing that. It's too Too much VOs or C's and square roots and all that garbage. So we just write it like that, right? So, right? So this is the gamma. So we just write that delta T equals gamma delta tau. Okay? That's how we're going to remember it. Now, we have names for these things, okay? Unfortunately, the names are pretty pathetic. They're kind of misleading. Oh, well, we just do our best, okay? Okay, so delta tau, which again is just, oh, forgot my delta over here, sorry. Okay, so delta tau, which is just delta t prime, right? That's the time measured in the moving in the S prime reference frame. Okay, so this delta tau, or delta t prime, that's called the proper time. There's nothing proper about it, but they just, I don't know why they named it that. But anyway, the proper time, you know, when you say a proper, you think it's like, you know, superior or something special. It's not. It's just the time measured in an S prime reference frame. But anyway, the proper time delta tau in a particular reference frame is the time interval, you have to know this by the way, is the time interval between two events that occur at the same point or the same location in that reference frame. When we get to do the relativity problems later on, one of the first things you have to figure out is which is the proper time, which is the other one. So you have to know this. So let's say it again. Proper time delta tau in a particular reference frame is the time interval between two events that occur at the same location in that reference frame. All right? So two events, it's okay, proper time, two events occur in the same location in that reference frame. All right. Now remember, gamma is greater than 1. So this is always, delta t is always going to be greater than the proper time, right? Okay. So the longer, they call it the dilated time. I'll show you why in a minute. So the longer dilated time, delta t, is the time interval between the same two events, but this time the events are measured in a second reference frame that has a speed v relative to the first frame. Okay, so here the two events will be at different points or different locations in this second reference frame, right? Okay, all right. Why do they call it dilated time? Have you ever gone to the optometrist and had your eyes checked? And what do they always do? They always dilate your pupils, right? So here's a normal pupil, an undilated pupil. Here's a dilated pupil, right? It's larger, you know? So the dilated time is always larger than the proper time because gamma is always greater than 1. Okay. By the way, you know, we got this equation using a light clock. It doesn't matter what kind of clock you use, you know. We just chose a light clock because it was easy. But our argument applies to time, okay? I don't care what kind of clock you use. We're talking about time, and so our argument works for time, all right? We just use a light clock, like I said, because it was easy. Okay, so, okay, what's the first, so here's the light clock thing, right? What's the first event? The first event is when the photon leaves the bottom here. What's the second event? When it returns here. Or, you know, we could have said that, but whatever, it's our choice, you know? So let's say this is the first event, this is the second event, all right? This is a nice way to explain it. You'll see what I mean in a minute, all right? So, in which reference frame do both events occur at the same location in that reference frame? Well, Velma, right? I mean, there's a foot, right? The photon leaves by our foot at the bottom of the light clock for this event, and it returns, right, by our foot by the bottom light clock. So both events happen at the same location in that one particular reference frame, you know? Okay? So who measures the proper time? Velma. Remember, that's a short one, right? Because she just says, bing, bing, you know? Okay. In which reference frame do the events happen at different locations? Well, Mort, right? First, Mort sees it way over here somewhere. then Mort sees it way over here somewhere, you know? So the two events in Mort's reference frame happen at different locations. So who's going to measure that longer dilated time, the delta t? Well, Mort, right? Mort will. Okay, so let's talk more about this. You are playing baseball near a playful bird, which flies past you just as you hit the ball. The bird continues to fly at a constant velocity, reaching an outfielder just as he catches the baseball. Okay? So the bird was there when you hit the ball travels with the bird was there when you hit the ball, the bird flies with the ball, then when the outfielder catches the ball, the bird is right there. All right. Which of the following statements is true? Number one, you measure the proper time of the hit, and the outfielder measures the proper time of the catch. 2, you measure the proper time interval between two events. 3, the outfielder measures the proper time interval between the two events. 4, the bird measures the proper time interval between the two events. Remember, for proper time, both events happen at the same location in your reference frame. So which one of these is true? This is one of these super important questions. So pause your video and figure it out. Okay, hopefully you got this one. Okay, so okay, the two events are the ball being hit and the ball being caught. So who or what was there at each of those events? The bird, right? The bird. So the bird measures the proper time. Okay, let's see. All right, let's just do a numerical example just for fun. So let's say we have a rocket, and this is, in our imaginary world, right? Let's say that the velocity of the rocket is 0.999999. Okay? So that means that the speed is 0.999999 times the speed of light. Agree? Okay. Now remember, gamma, right? So gamma is 1 minus beta squared to the minus 1/2 power, right? Or it's just this, right? I like writing it like this is shorter, you know what I mean? But whatever, who cares? Well, that's what, all right? So if you use your calculator and you figure that out, so you get 1 minus 0.999999 squared to the minus 1/2 power. So you get 707. Okay? So what does that mean? That means Velma, she just measures her second, and she's right. But what would Mort measure? Mort would say it takes 707 seconds to go from the bottom light clock back. All right, think about it. Velma, 1 second. Mort, 707 seconds. I mean, that's a big difference, right? So that's kind of cool. By the way, 707 seconds is 11.8 minutes. So think about it. Velma, 1 second. Mort, almost 12 minutes. And again, you look at this graph. 707 seconds, that's way up there, right? That's way up there. So that's why it's nice to have the equation, not just the, anyway. Okay? Cool. All right, let's quit.